of how Multicore OCaml went from an idea to an actual thing that we could use in production. And in part, what I want to talk about is the kind of particular technical things that we learned along the way as we kind of went through this process of trying to productionize this work here. And in part, talk about the kind of broader story of technology transfer, of like what it takes to take an idea and a good set of work that's been done in an academic context and move that into a large-scale industrial production use, and the things that you learn along the way doing that. And I want to start with a paper, right? Appropriately, here we are at, I guess, a mix of ICFP and Uppsala, and there was a nice paper in ICFP in 2020 called Retrofitting Parallelism onto OCaml that really kind of went through this whole like design and set of ideas. And the goals of the paper were to produce a modern, high-performance, multi-core garbage collector that would fit into the OCaml ecosystem. And critically, the idea is that this design should be both easy to maintain and easy to adopt, easy for people who were using the pre-Multicore OCaml to pick it up and have it work for them. So on the subject of maintainability, part of the design here was to have only one runtime to maintain. Programming languages are outrageously expensive to maintain. Every part of them is very expensive. There's a lot of engineering and work that goes into each and every one of these. And having just a single runtime that would work for both parallel and sequential workloads was part of what they wanted to achieve. And to make it easy for people to adopt, they needed to preserve sequential performance. So you could take your program that was written before Multicore and use it on the Multicore GC, and it should still perform pretty well. And not just the overall performance, but also the pause times induced by the garbage collector. This is really important if you want to be able to write good, soft, real-time applications to kind of preserve the behavior. And in fact, OCaml has an incremental garbage collector. It does a good job of having relatively small pause times, which is good if you want to build soft, real-time applications, which it turns out at Jane Street we do. And also you want to preserve the FFI, if possible, because all the code written against your FFI is already wrong, and then you have to like maintain it and move it to a new FFI with subtly different semantics, and it's going to be an enormous amount of pain and suffering and a source of many bugs. Another thing the paper did is it produced a bunch of benchmarks and evaluations to see whether or not it really met the goals. And if you looked at those evaluations, it looked like something like a few percentage points of loss of performance for sequential programs, which was thought to be a kind of acceptable loss in that case. It's worth saying, you shouldn't talk about the performance of a garbage collector as a single number. Garbage collectors are really a curve, right? There's a kind of there's a trade-off between space and time, so you need to think about both of them together. But the benchmark showed relatively similar memory usage, also similar pause times, and overall good parallel speedups, right? You sort of were able to, in fact, throw multiple cores at problems and have things go faster. So all of that was pretty good. So it did, though, kind of take a while. So yeah, 2013, the project was born. There's a number of papers marked in green that were written. This is not an accidental feature. If you would like to get your fancy new feature accepted into OCaml, you might want to write some papers. So 2015, there was a paper at the OCaml workshop about effect handlers. There's the retrofitting parallelism to OCaml one that I mentioned before, and then another one, retrofitting effect handlers to OCaml, published in 2021. There's this Sandmark benchmark suite that was an important part of like figuring out whether they were hitting the performance goals at all. And then in 2020, like the upstream team was like, all right, we're doing this. We're going to upstream this thing. We got to actually get it done. And finally, in 2022, OCaml 5 was released. It had multi-core GC and effects, and we're done, right? It's simple to maintain. It's easy to adopt. We're all done. Well, yeah. So then there's like another 2.5 years of stuff, and like, in some sense, this talk is about those 2.5 years and like why they're there and what they came from. Some of it's kind of straightforward. Like if you look at the things in blue, those are all features that had to be backported to, or forward ported, whatever, brought back after they had been deleted. Because it turns out, we'd been working on the garbage collector. Various improvements had landed during this like long process of generating the new Multicore GC. And so there was this like very cool optimization of adding software prefetching, which it turns out if you do it just right, rather than getting like a 20 to 30% win, which is sort of what you see in the literature, we actually got like 2 to 3x multipliers in speed. So that was kind of awesome. Definitely needed to get that back. Compaction had been not done in the first version, that had to be added in. There was this very cool stat-memprof, statistical memory profiling facility, that had to be brought back. But then like there's some other things that happened where we had to like switch to a new runtime, and there was this rather awkward thing of there's a new language, which was different in a number of ways from the old language, with a new runtime. And it's like, well, you should just switch to the new runtime. It's like, no, right? You can't do that because the new runtime is very different. You have to actually have some period of experimentation and seeing whether or not it causes problems. So we did a bunch of work back in 2023 to get what we call OCaml 5 minus. It's like the OCaml 5 language with the old OCaml 4 runtime, and then eventually with the ability to choose between the two runtimes so we could compare their performance. And then we compared their performance and like, we're not happy. Like it turned out there were real performance regressions that like hadn't been clear before. And then there was like a lot of work, and then here we are, 2025, and earlier this year, finally like, it was announced to be sort of at general availability within Jane Street, and we were able to start using it. And kind of the question is like, what happened? Like why did we, both like what did we discover along the way, and like how did we get into this spot? All right, so first of all, I should talk about who did the work. Here I am talking about it, but I have done nothing. But so there was a bunch of the original academic work that was done, and kind of the names on the paper. And then in the last 2.5 years, there was a bunch of people mostly at Jane Street, and with some collaboration with some of the other folk who did the kind of the original work. But like this was kind of the focus of a number of people just like doing a lot of experimentation and work to figure out and understand these problems. So all the work is from them. All the mistakes in presentation are mine. What I want to do is just start by talking about what is going on, what the differences are between the two versions. I'm going to like, in a number of places, give you like a tour of like what things were like in runtime 4 and what things are like in runtime 5 and how they differ, and then we'll talk about some of the things we discovered. So, what is runtime 4 like? First of all, it's sequential. That's what this whole talk is about, right? It used to be sequential, now it's parallel. It's also generational, right? There's the good old generational hypothesis. It's a surprisingly robust finding across many different programming languages that most memory dies young. And on the basis of that, you can have a generational collector where you have a minor heap and a major heap, where the idea is that the minor heap, most of these young allocations will never escape from the minor heap to the major heap. So on the minor heap, you can use a brutally simple allocator. An allocation in OCaml is 3 machine instructions and is very fast. And then when you get to the end of the minor heap, you just kind of copy the survivors, and because of the generational hypothesis, there aren't many survivors, to the major heap. And then the major heap is a kind of traditional mark and sweep collector. And then one additional important piece is, in order to be able to collect the minor heap, you kind of need to not have to trace everything to know what is still alive on the minor heap. If you were in a lovely, pure functional programming language with no, dirty mutation or laziness or anything like that, you would have the nice property that everything in the minor heap would have no point. You'd have no pointers from the major heap to the minor heap, right? Because like everything in the minor heap is newer than everything on the major heap. Right? And therefore, you'd need mutations to get like arrows going in the wrong directions. But of course, we do have mutations, and so you add a write barrier, which is on the mutations you check whether it is introducing a back pointer from the major to the minor, and then you're going to track that separately, essentially as an extra route for the traversal of the minor heap to make sure that you can actually detect what is in fact alive. To talk a little bit more about what is a mark and sweep collector, it's a familiar topic, but just to remind everyone, what do? It's you got a mark phase and a sweep phase. The mark phase is you start from the roots and you kind of do a traversal of the whole heap, marking all reachable objects. And then you do a sweep phase where you walk over the heap, collecting all the things that you have now shown to be unreachable. And just to remind everyone what's going on there. Sorry, wrong diagram. So in blue we have the roots, and then we have all these blocks on the heap with arrows between them, and you just start doing a traversal bit by bit, and turning from, as you kind of do the walk through the tree, turning from red to green, basically from unmarked to mark. And as you get to the end of that, then everything that is still red is stuff that you know is gone. So it's the end of the mark phase, and then you get into the sweep phase, and now instead of walking over the object graph, you just walk over all of memory. And like you hit anything that's marked, and you're like, well, that's going to stick around, and next time we're going to have to do this again. So let's make it unmarked. And then every time you see something that is unmarked, you're like, well, that's done, and I'm going to free it, right? And then you just kind of keep on doing that through the rest of the heap, and when you're done with the whole cycle, and you can start again, right? So that's like the basic story of a mark and sweep garbage collector. It's not quite, at OCaml, quite so simple. That like shows everything happening in one phase. Actually, the OCaml garbage collector is incremental, right? Which is to say, you can break up both the marking and sweeping phases into what are called slices, little bits of work you can do at a time, so you can have the pauses that are imposed be small. There's some extra overhead from doing that, but it makes the resulting system much better for any kind of soft real-time thing. And actually, you need this. It's like insane not to have. You're going to have like multi-gigabyte heaps and no way of incrementally scanning them. It's just like you can't build, it's not like, you don't have to be worried about like writing trading systems, like you can't build a UI. It's just like too bad. So the incremental stuff is really important. And then one other important part of the design is the design is built on what's called a snapshot at the beginning invariant, which means when you think, what does it mean for the collector to be correct? What does it have to collect? And the idea is, well, anything that was allocated at the beginning that's unreachable should be collected by the end, right? And the point is you don't necessarily have to collect, you're not obligated to collect things that are allocated along the way. This turns out to be, it's not the only way to build a garbage collector, but it's a useful invariant because it means that you kind of have a bound on how long it is going to take for the collector to get to the end and finish and actually collect things. Of course, you only actually do the freeing when you get to the end of the cycle. Right? All right, so that's runtime 4. Let's talk about runtime 5. And maybe the first thing to know about runtime 5 is it's a lot like runtime 4. Many of the properties are preserved, but it changes in some important ways. Maybe most importantly, parallel, right? It's now a parallel collector. And in order to make that parallelism work, there are, part of the story here is there's some stop the world phases, some spots in the collection algorithm where all of the different threads that are running have to coordinate and kind of hit a barrier in order to kind of make progress from there. And then in order to make that work in an adequately performant way, there are safe points, right? You have to make sure to insert spots into every program which will stop and check in with a garbage collector. So among other things, it can actually participate in these barriers, right? If some thread kind of can't get to the point of getting to the barrier, the whole system gets slowed down. And you basically do things like add a safe point at the back edge of loops and things like that. But you want to make sure that like reasonably often you're going to have these safe points that interrupt the running of the GC. Again, we have a minor heap, but actually minor heaps, multiple, one minor heap per thread, per core that you have. And in the minor heaps, we're going to do a stop the world collection. So all the minor heaps, this is one of these kind of stop the world phases, all the minor heaps are going to collect together. Notably, like some might finish earlier, like different threads might be allocating different amounts. So the ones that finish early just like spend some extra time collecting the major heaps so they don't waste their time, but they really do all have to get to the end in order to move on. And then we have the major heap. And the minor heap is basically not shared, right? It is meant to be separate, one per domain, and the reason for that is to avoid the costs of synchronizing a bunch on those, because you want to make the minor allocations as fast as possible. But all the shared stuff ends up going into the major heap. And an interesting detail of this is they ended up with a merged mark sweep design. So instead of having a mark phase and a sweep phase, there's like a sweep and mark phase. And this design idea was stolen from the very concurrent garbage collector. And the idea is, well, these synchronizations, those sound expensive. Let's have fewer of them. And so by merging the two together, you get to have one less synchronization point. Right, and again, at the end of that, there's a little stop the world synchronization, kind of at the end of the merged mark sweep cycle, but just one. So let's talk a little bit about, we sort of talked at a high level, let's kind of remind ourselves how this whole GC color thing works, right? The colors are these like little state bits that we have that we kind of manipulate as we wander around. So in runtime 4, there's a marking phase when you move unmarked blocks to being marked blocks. And then there's a sweeping phase where unmarked blocks are made free and marked blocks are made unmarked. Okay? Runtime 5 is different. There's a marking phase, or rather there's marking activity. There's not phases, right? Sometimes you're doing marking, sometimes you're doing sweeping. When you're marking, you're moving unmarked to mark. When you're sweeping, you're moving garbage to free. So there's an extra color, there's an extra identifier, right? Some things are explicitly marked as garbage. And so there's like something obviously nice about this, which is to say you can just kind of tell from looking at these transition diagrams that you can intermix the marking and the sweeping because they're not touching the same colors. So they're kind of not going to interfere with each other. But that's also bad, right? Because you actually need things to move from being marked to later being swept. So somehow you have to like tie the knot. And that's what the thing that happens at the cycle end is, right? Which is you have this cycle where you want to take all the unmarked things and make them garbage, and all the garbage and make it marked, and all the marked and make it unmarked. But instead of, like in the previous diagram, doing this by walking through and changing the colors, you just, the colors are just a state of mind. You basically like have a constant amount of space that tells you like which bit pattern means which thing, and you just like atomically switch it, and like in some sense the meaning of all the bit patterns changes, and you don't change the physical bit patterns, but the one that used to mean unmarked now means garbage, the one that used to mean garbage means marked, and so on and so forth. So let me just pause for a moment, because I've said like a lot of things about the garbage collectors. Like, are there any questions about like the details of like, there's a lot of details. You can understand various pieces of this without maybe understanding all of them, but like anything anyone is like confused about, or there's some of the people who worked on this paper, they can tell me I'm wrong. Like, is there any? All right.
Do I understand right that at the moment where you like change your at the moment where you change your interpretation from interpreting some bits of as like meaning garbage to meaning marked, there's nothing that actually has those exact bits?
Oh no. No, there are things that have those bits, right? But the whole point is it's like the thing you semantically want to do is you want to like recolor things, but you kind of do it atomically for the entire set of things by just kind of locking the place where the interpretation is stored and changing the interpretation. But yeah, you've kind of gone through this phase, and there were things that were unmarked, and you put them as marked, and now those things that are marked, you want them to be unmarked for the next cycle, and yeah, it changes them, so they are now unmarked for the next cycle.
Oh, sorry, what I mean is like specifically for garbage, you've like freed everything that was marked as garbage. So
yes, that's right. So the garbage one in particular is gone. So it's like we are just moving that one because we want to use the bit pattern, but that one there are no things that actually need to be in that stage.
Thanks.
Yeah.
I've forgotten how it works in OCaml. How do you know what's shared and not shared? Like how do objects become in the part of the shared heap?
Right. So, and this is like a thing that I actually don't really remember. That there's probably people in the audience who will do a better job of this. But there's like a kind of discipline where you basically detect dynamically that some things are shared and can promote them to the major heap. And
Now it already is kind of shared, right? But there's nothing you can't like stuff on the minor heap can be pointed to from other minor heaps. There's no hard boundary between shared and unshared.
Sorry, a thing Ron didn't mention is the first paper had 2 different garbage collectors
Yes.
in it, and he's just quoted something from the wrong
Wait,
one.
aren't there? But if you mutate them, don't you have to move them? I thought there was a stage where you did have. No, now there's just no moving. Got it.
You don't have to change the after 5 of the other one.
Right. Yeah, it's good to have the actual experts in the audience. All right. Okay. So now let's talk about what went wrong. So remember I said you need to think about the curve of the performance of a garbage collector. It might be better in CPU terms and worse in memory usage, or the other way around. This one was worse in both. So we found some programs were like 10 to 20% slower, and for those of you who are paying attention closely, that's more than 3%. And And then also, excitingly, some programs were using 10 to 20% more memory. And actually, these were like things we saw in some early benchmarks, but like you could come up with benchmarks that were much worse, right, in various things. So that was like distressing. Like this was like not the shape of a thing that we could in fact roll. And it's clear, some programs, there was like variation between the different programs that you ran. Some were affected a lot, some not very much. And where did this come from? And there's like a much longer version of this talk I could do. I mean, I could do if I was more competent. So maybe like we could collectively do a several-hour version of this, of like going through all the different things that were discovered and how we did. But like just to give a high-level summary of things that we found. So first of all, there were some problems in pacing in the GC that were subtly different between the two collectors that we had to work through. There was also like a long, kind of hilarious sequence of problems with transparent huge pages, where, you know, the old garbage collector had been invented before huge pages. You say, what are huge pages, right? In the 1970s, when God invented Unix, right, pages were 4K, and we were all going to be happy with that, except hardware changed a lot, and 4K is an insanely small page size. So there are these larger pages, 2 megabytes, but like rather than like switching the system to it in some kind of general way, there's like a bunch of clever stuff in the OS to automatically allocate for you these kind of agglomerated huge pages instead that are 2 gigabytes typically. And like, you know, Stephen Dolan can tell you a bunch of stories about how broken this has been for many years in the Linux kernel, where like that system for doing it was like kind of awful for a very long time. But anyway, the original garbage collector was designed before there were transparent huge pages, and therefore worked very well with it. And the new garbage collector was designed after there were transparent huge pages, and therefore worked very poorly with it. Anyway, there's a whole complicated story about how that happened, which I won't go into, but that's one of the fun things we hit. There was also just like, there's the new parallelism that we have with domains, and the old parallelism with systhreads, and like they were integrated in not quite the right way, and there was a bunch of like annoying extra overhead there that we discovered. Also, there's this like heavyweight domain thing. We also have a new lightweight thread notion. Then this kind of threadlet thing had its own notion of stacks, which were different from the old stacks. And there are checks to know whether you've gotten over the edge of the stack. And like the new ones were kind of slow. That was another issue that we ran into. And just generally, like parts of the code were not as fast, right? Like the old code had like, you know, been beaten into shape over a long period of time. And there were just like places where it wasn't engineered as well as possible. So I'm not going to like go over like this entire list and talk about it because it's a lot. I mostly want to talk about the pacing. There's like an interesting story there about we learned about GC pacing, and it's kind of enough to give an illustration of the kind of things we were doing and learning from here. So let's talk about pacing and how it worked in runtime 4 and then how it works in runtime 5. So on this, there's kind of two kinds of memory we're going to talk about. There's memory allocated on the sort of ordinary garbage collected heap, and then it turns out we sometimes care about off-heap memory. So we'll talk about both of those. The approaches are pretty different. On-heap memory, well, there's a question of, I said there's that curve, right, about like how you trade off space for time. You have to decide how you're going to configure your system to make that trade-off, and there are different ways. Like classic garbage collector papers are all about Java, and Java, you know, hulking enterprise Java had like a hulking enterprise model for doing this, and you have like a roofline model, meaning like you're going to run your Java program on a box, just one program, right? And it's going to use the whole box. So just like tell it how much memory you have, and it will trade off space with time to avoid exceeding that total memory. That is not what OCaml did, and it's kind of not great for like how we use OCaml for like a lot of stuff. Sometimes for like big hulking enterprise program that takes over a whole box, and sometimes for a million little programs that do a lot of different things. And so instead of trying to configure it in this roofline model, there's this notion of space overhead. You just ask, you know, how much extra wastage in percentage terms are you willing to tolerate, and that's what we're going to target. So that's the basic tuning idea. And the way this is done is based on what's called a steady state assumption. So what you're going to do is like think back in your armchairs, like how might this work? I'm running a program. Let's say I'm running it for a long time. How much might it be collecting? How much does it need to collect? Well, it's like, well, if it's running for a long time, like it can't use an infinite amount of memory. So like the amount it's collecting has to be basically the amount it's allocating. So we could like just make the assumption that we need to like collect as much as we're allocating, and then all that separates us from a way of doing the pacing is some high school algebra. We can just like set up some equations and work it out and like come up with a number, and that's basically what happens. It turns out, in a lovely way, you do the high school algebra and like stuff cancels out satisfyingly, and you discover that you can just do a constant amount of collection, some marking and some sweeping, which you can sort of measure in like number of bytes you have to mark or sweep versus number of bytes you allocated, per word promoted, right? So remember, there are like two parts of the garbage collector. There's like the minor allocations, but the ones that matter for clocking the major heap are promotions to the major heap. We kind of don't care about the minor heap when we're thinking about the major heap. Okay, so that's how that part works. And now what about off-heap memory? So first of all, what do I mean off-heap memory? So for various reasons, you want to kind of take responsibility for memory that is not managed in the ordinary way of OCaml. Maybe it's because you're doing I/O and you want like regions of memory that aren't going to get moved around. Or maybe you're using some third-party library and you want your like PyTorch tensors or your like GMP numbers or whatever to be taken care of like off the heap because you don't have control over those. Like there's just some other library you're interfacing with that's actually responsible for that. But kind of the garbage collector is responsible for collecting those, because the way you do it is you like have a garbage collected value that's a points to, that's responsible for the off-heap memory, and then when that gets collected, well then you're going to like do the free to get rid of that stuff that's off-heap. So the garbage collector really is responsible for and needs to be clocked in part by the need to collect the off-heap stuff. So what are we going to do? Well, here's what we did, or what the long ago Damien Doliger did. There's an extra, just a number called extra heap resources. Think of it as a number that goes from 0 to 1, and we're going to use this number to determine when we have like a whole extra cycle worth of work to do. So we're going to increment this extra heap resources by this little n over kh equation every time we do an allocation. So n is like the amount allocated by that allocation. H is the overall size of the garbage collected heap, and k is like some constant to like, which is going to tell you how fast you should be going. And like the kind of rough intuition about how this, like why this kind of makes sense is like, if you have like an amount of extra stuff roughly proportional to the amount on the heap, then you kind of want to collect the whole heap, right? Like that sort of incentivizes you at kind of roughly that ratio. And if you want like a better, more principled argument as to why this is a good idea, I'm going to disappoint you because there isn't one, and it turns out it's not a good idea. But anyway, it's what we did, right? Okay, so this all makes me want to talk a little bit about control theory, right? Because like, what do we got here? We've got a system where we are trying to like control some process by kind of making measurements in the world and deciding how fast to work to kind of keep some dynamic system in control. And when you build these kind of systems, it's worth distinguishing between open loop and closed loop control. So what do I mean by that? So an open loop control system is one where you observe something about the world, and those drive some set of decisions that you make. But the decisions you make do not affect the quantities that you're observing, right? It's an open loop. You just like make decisions based on what you see. So why might you like an open loop system? Well, they're like kind of predictable and easy to manage, but a big problem with them is they don't necessarily do what you want to do, right? Like in some sense you are aiming towards a target, you're trying to modify, you're trying to move a target, and because you're trying to modify it, if you want to be open loop, you can't look at the thing you're trying to modify. That's what it means to be open loop. So a kind of a little more predictable, but like harder to like get to do exactly what you want to do. And there are closed loop systems. In a closed loop system, well, it's just like the opposite. You get to observe the quantity that you are trying to target for. So what's good about these is you can really zero in exactly on the target. And what's bad is like, I don't know if you've ever done like high school robotics, but you're now in like PID controller hell. It's like, you gotta like tune the parameters, and if you're like too aggressive, you end up like oscillating back and forth as you try to get there. And if you're unaggressive enough, it takes a long time to converge, and it's just kind of no fun, right? So, and if you look back at the design we talked about, the heap pacing turns out to be open loop, right? Delightfully, terms like the size of the heap just kind of canceled out in our high school algebra. It's a lot of high school algebra, high school robotics, anyway. But the off-heap pacing is closed loop, because we're looking at that capital H. Like that's a quantity that we're controlling and we're responding to. Okay, so this will matter later, but I just want to like lay those ideas out there. Now let's talk about the results. Like, how did this thing work in like runtime 4? So here, so first of all, I just want to like lay out what this graph is supposed to show. There's no data here yet, but on the x-axis we have this the space overhead we requested, right? So like 100 in this graph means I think you can like you can up to double, have like up to a factor of 2 extra memory, and then we can measure like what's the space overhead we got, right? And then what do those lines look like? So it turns out they look like this. So there are 3 different lines. The ones that are like kind of close to the black line are benchmarks where we're like allocating a lot of lists or we're allocating like a bunch of strings. And there's some interesting stuff going on there. There's like some like weird like stair step thing going on, and that's mostly because the system has like it doesn't like grow the heap in little bits. It grows the heap in big chunks, it turns out. And so that's it. But it's like pretty close. It's sort of doing approximately the right thing. Our control equations seem like they're like not terrible predictions of real life. And then there's that horrifying line on the bottom. And that's a benchmark which is really, really aggressively allocating external memory, these big arrays. And there, what you see is, like, it's just not responding to the control thing at all, and the garbage collector is working super hard all the time to collect as much as it can, right? So parts of this work well, parts of it are horrifically broken. And it's worth saying, this is runtime 4. They were horrifically broken before we started, and this is a real serious problem. Like, we have spent at Jane Street like quite a lot of time wrestling with bad garbage collector behavior, specifically around this external memory, and have tried over the years various different kind of hacks to improve the behavior of the GC to fix this, and not being enormously successful in that. All right, so that's how runtime 5 looks when you use it. How does runtime 5 look? Well, so for ordinary on-heap allocations, the pacing story is basically the same basic equations. But here we are in the garbage collector. We like looked at things and like we fixed some stuff. There were some bugs actually in the original implementation. Notably, one of the fun bugs was instead of clocking the decisions about external memory were made for every allocated block, not for every allocated block that's on the major heap. So like that benchmark that's very, very aggressively allocating big arrays, like most of them are disappearing on the minor heap and never getting to the major heap. You shouldn't be doing any collection on the major heap for those. They just don't matter, but it does it anyway. So that was like, and we fixed that and a few other bugs in the implementation. I should also mention every time I say we, I did none of this work, but the royal we did this work. And then now we can see, okay, what are the results of that? How does runtime 5 actually look in practice? And it's like not what we wanted. This is not good behavior. So like the byte and list allocations are like screaming up high, so they're using way more memory than they should be. And then there's like the external memory, which looks like a little better, I guess. It's like, it's not nearly as aggressive, basically because we fixed that thing with the kind of minor heap stuff, but it's still like not responding at all linearly to the control thing. So this is not going well, right? And this is like, you try to roll this into production and like bad things will happen. Like things that ran yesterday will like and crash and stuff. So this is like.
And we did try to roll into production a little too early.
That's right, yes.
And they did do.
That's right. As Leo points out, this is not like a theoretical, it would have been bad. It was bad. We did it in production and it didn't go well and rolled it back. Okay, so we're like, oh, this is not good. What are we going to do about this? And
Did that result in real loss of money?
I don't know. Lots of things go wrong at small scales. I don't. So what happened? So first of all, it turns out ordinary collection was just less aggressive in the new GC than in the old GC in a way that like we kind of knew but hadn't like been totally thinking about. Like the people who wrote the paper were not unaware of this change in the design, but like it was just kind of a bigger effect than people were quite like counting on and thinking about. So just to illustrate what's going on here. So here we are talking about garbage collection, so my graph doesn't show, there's the interesting part of the system, which is the garbage collector, and then there's the mutator. It's like that user program that nobody cares about, right? We're just here to talk about garbage collection, so I don't even picture the mutator on here. This is just the garbage collection phases, right? So in runtime 4, you have these sequence, sweep mark, sweep mark, sweep mark, and then you think if I allocate something, how long does it stay alive for? So if I allocate something in the middle of the sweep phase, well, it's not going to get collected in the sweep phase. In the mark phase, by the end of the mark phase, you're going to know it has to be freed. And then by the time you get to the middle of the sweep phase, somewhere in there, you're going to collect it. So you basically wait kind of one full cycle's worth of time to collect something that was allocated at some random point in the sweep phase. If you allocate something in the mark phase, well, because of the snapshot at the beginning thing, it's not going to get collected in that mark phase. It's not even going to get marked by the end of that mark phase. It's going to get marked at the next mark phase, and then only swept up at the sweep that follows that. So we're going to take 1.5 cycles for that. So basically 1 1/4 cycles is how long you're going to have floating garbage, right? Things that have been allocated and aren't yet collected, even though they could be. So what about the merged kind of VCGC, very concurrent garbage collector style system? So here again we have these merged sweep mark phases, but it's worth saying it's not totally uniformly distributed sweep and mark. You mostly sweep in the beginning and mostly mark at the end, and the edges can be a little blurry because you haven't synchronized. So we can kind of again ask the question of if we allocate in the beginning of the sweep, what happens? Well, it has to get to the end of a full marking phase, and then to the middle of the sweep phase of the next merged phase after that. So that's going to take 2 full cycles to get collected. And if you allocate something in the middle of the marky part of the sweep mark phase, well, that's actually going to take 1.5 cycles. So that 1.5 is kind of the same as before, but the allocated in the middle of the sweep phase is a lot worse. So it went from 1 1/4 to 1.75, and that's a big change to how fast the collector is running.
That's a stupid question when you say, stupid question when you say allocate, you actually mean forget, right, or drop.
Sorry, yeah, that's right. I guess a thing that it's really a thing that becomes ready to be collected. That's right. That's a better way of saying it. All right. Okay, does this picture roughly make sense to people? All right. So that was a problem. And then we decided to fix that by basically saying, you know what, that part of the VCGC thing, maybe that was just a mistake. We just broke them up into separate phases, one extra synchronization. Actually, one thing we kind of learned along the way is the synchronizations we were worried about is actually kind of cheap. They're actually not that expensive. Having an extra one is not so bad. And they kind of scale pretty well. Roughly you should expect them to grow in cost with the log of the number of concurrent domains you're running. So it's at the scales we're talking about, just kind of not that big of a deal to add one extra, and it makes making the collection much more aggressive is just worth a lot, because otherwise you have to do a lot more GC in order to make things happen. So as I said, the excessive collection with big strings is better because we fixed that bug. And that bug fix made the allocation less aggressive, which made it better. But it's worth noting there were others that made it more aggressive. And a general theme of this work is there are a bunch of things that are wrong, some of them offsetting. And then people are depending on it. And at this point, the bugs are load-bearing, right? The entire ecosystem has adjusted to the behavior of the system. And when you change it, even in ways that are good, some things might not go well, and especially when you change it in bad ways. So it's just a complicated place to engineer. All right, so we did this mark delay patch. What do things look like now? Better-ish, right? Some things are the green lines are still not that close to the black line. They're still curving somewhat uncomfortably away. The bottom green line for the off-heat memory thing is worse now because we've made, mark delay has now made things more aggressive, so this is now more extra fast than you want it to be. So we're still pretty unhappy at the state of things. We fixed stuff kind of, but the world is not in a good place. So what do we do now? Where we're okay, look, we tried to fix some of the implementation bugs before. Maybe we should fix some of the design bugs. And in particular, one thing that was noticed is this n over kh equation. was kind of wrong. Like the H was the wrong H. It was it was like the amount of memory in the garbage collected heap. But you kind of want to, it makes more sense to think of like the kind of memory in the overall heap. That seemed like, again, there's no good principal argument for why this is exactly right, but that seemed like a step in the right direction. Like the really pathological case was where this ratio was super high, where you have lots of off-heap memory and very little on-heap memory, and then you just like insanely want to allocate over all the time, even though actually there's very little to walk. So you're just like constantly walking this tiny heap, and it just makes no sense. So we thought we could fix that. But like this wasn't great either, because now we're like in a world where we're dealing with this like closed loop control system, and it's again like hard to get right and hard to tune in the right direction. So what did we do? We basically took the last possible resort and decided to think deeply about the problem, and in particular be like, well, maybe like this n over kh thing, like did that make any sense? Like why did we do that thing? And like people went back to like what actually would make sense from a more fundamental perspective, and let's like think a little more precisely about how the garbage collector really works, try and get the high school algebra a little more right, and go back and rethink the steady state analysis. And like, kind of to everyone's surprise, there was a really nice solution, and it was an open loop solution for both parts, which I just want to emphasize, we know no good reason why this had to be true. It's just like the math kind of worked out, things canceled. And like you ended up with a nice solution. And it doesn't, I mean, it kind of makes sense. Like you ended up with constant number of words collected per word allocated. But notably, there's an extra word of sweeping when something is on heap, which kind of makes sense because you don't actually need to sweep the off heap stuff, right? So like, there was no quite reason for it to work out this nicely, but also like the end result is like kind of coherent. And then we tried it. What does it look like? And like, I'm not sure if I can convey what a feeling of like warm comfort and relaxation I get from those blue lines. Like, they have the right angle, they're relatively close to being on target, right? And some of why this is right is like, yeah, and also like there isn't this like disaster for off-heap memory. It's like it all just kind of works nicely together. And like some of this being more on target is like the fixing of the off-heap thing. Some is just like a little bit more like care and accuracy in understanding like actually how exactly does the garbage collector behave, and like getting the setup of the equations that you then applied the high school algebra to just right. Right? Okay, so this was like a very satisfying end result.
It's still diverging, though. Is this a happy ending?
Yeah, I think this is a happy ending. It's diverging a little bit, but it's not like curving away. And it's maybe worth saying like, you don't have to get it exactly right. Like, I think part of the observation of why you prefer open loop control to closed loop control is you actually don't care that much if you exactly hit the target, but what you want is a knob that works and works predictably. And even if it's a little off, even if it's off by like, a little, the slope's a little off, like you still get a knob that you can turn. And like that's actually the most important thing that you want out of a system. Okay, so that's like the end of like the deep technical stuff that we were doing. Like what did we learn like at a meta level from this whole process? So one thing is like benchmarking is super hard, like hard to get right. And I think the original testing that like went into the paper just leaned too much on small programs. And it just turns out like different programs put different pressure on the design, and it really matters what things you measure. I think actually there's an interesting like structural thing about how the paper and the original implementation was set up that kind of made this happen, because like what kind of benchmarking are you going to do? The kind of benchmarking that you can practically do, right? And one thing that made benchmarking real serious big programs hard is there was only one runtime, right? Which per thing. So if you wanted to like compare the two runtimes against each other, you had to use two different branches of OCaml with two different languages, right? The language has evolved a little bit. And when you add new features to your language, people start using them. And so we didn't have like a corpus of programs that you could reliably, easily run on both of these. So like part of what Sandmark did was some careful curation of like programs that would work nicely on both systems and kind of keeping them up to date and working in both places. And that's a pain in the ass. Like nobody wants to maintain a big program in that form. And so it like pushed in the direction of less serious performance evaluation. And like, I think it would have been better to not do that and to prioritize more, like understand in the end we have to delete the other runtime, but prioritize more the ability to really do the like-for-like comparison and do it on more serious programs. Another point is that performance debugging is hard. Like, you know, you're going to have a new runtime. It's a complicated system. Many things are going to be wrong. And the different things that are going to be wrong will cover each other up. Like the biggest one makes it hard to see the other ones underneath. And then also fixing the performance problems are wrong. And we made one part of how we did that is we would like look at what the problems were and then build a nice high quality improvement to try and resolve that problem. And that was a mistake. We should have written bad code to solve that problem. What you want to do is like do a bunch of relatively quick experimental ways of seeing whether this thing actually moves the needle so you can like explore and experiment more quickly rather than putting a lot of polish into a solution for a thing like, oh, that wasn't the problem. That's not exciting. And the other thing is just like, you know, being able to like pin the problem and separate the pieces. We also probably should have done a bunch of more little focused benchmarks that like picked apart the particular misbehaviors so you could understand and analyze them independently and be able to attack them in parallel rather than like in serial solving kind of one after the other. Another observation is like, you know, sometimes you should stop and think, right? I think that like we had just gotten so used to the off-heap thing being bad that like we hadn't thought maybe it could be good and like really spend the kind of hard thinking effort to go off and like see if we could solve this in a fundamental way. And it turned out in this case, delightfully, that a first principles approach like really solved the problem and didn't just solve like, you know, make runtime 5 better, but it like solved problems that had been pre-existing, had been bothering us for like the 20 years prior. Another point is backwards compatibility is hard, right? Every change you do is going to break somebody's workflow. The whole problem of load-bearing bugs just makes it hard to make changes. There's like a lot, it's a big, complicated business with a lot of software behind it. And like, it's just hard to make any kind of changes there. So you just have to be really careful and thoughtful when you do all of that work. All right, so what's next? How did this paper start? How did this talk start? There's like a good paper that was written with like some good work and idea, and then like a long series of painful hijinks as one discovered problems with that. So we're beginning the cycle again. We have this nice paper, Data Race Freedom a la Mode, which came out, won the Distinguished Paper Award in POPL 2025, which basically talks about the second half of this work. You know, part one, the runtime capability to have parallel programs. Part two, a programming model that doesn't make you want to tear your eyes out, right? And so here, the whole point of this is to use this kind of system of modes that we've developed to give type-level guarantees of data race freedom, so you actually have a way of reliably using this kind of system. And there's a lot of work that we're doing to take this idea and move it into actual production. So there's a lot of propagating type information through our libraries, which is like surprisingly hard and tricky. It's in part hard because like ML has a very rich system for like specifying complex interfaces with functors and the like, and like figuring out how to kind of wire things through that is hard. It's in part hard because frustratingly the type system discovers data races and then you have to fix them. So there's a lot of work that comes from that. Also, like, we've never built high performance concurrent data structures, and we need some, so there's a bunch of effort going into building those. One of the nice things about, we mentioned effects, one of the nice things about the original Multicore design is it puts the scheduling work in user space, right? So you can just write libraries that are schedulers, and there's a lot of interesting things to do in building good user level schedulers that can like do a good job of like adaptively solving problems for you. So you know, one of the like standard problems you have in writing high performance parallel programs, right? Parallel programming is terrible, right? It's terrible because data races are hard to avoid. It's terrible because it's hard to pick the granularity of the jobs that you want. You make it too fine-grained and you're swallowed in overhead. You make it too coarse-grained and you can't take advantage of parallelism. So that's like an annoying problem. It's also hard to know like how many threads you can use concurrently. And so there's a bunch of work that we're doing to try and like, you know, some more like, you know, adaptive control theory kind of stuff and clever implementation techniques to make it so that people can write relatively simple straight ahead programs that like, please parallelize my stuff and have something reasonable happen. Another thing that's terrible about writing parallel programs is they are really hard to understand. We have a, you know, there's shared memory parallelism. No, there isn't. There's like some weird message passing thing which is like dressed up as shared memory parallelism. You're shearing cache lines left and right and it's very hard to understand what's going on. And so like one of the things you want to do is have reasonable profiling and analysis tools that give you insights so like programmers can figure out why their programs are slow and fix them. Also, you know, there's both parallelism and concurrency, right? You can think of parallelism as when you have a bunch of stuff that you could do in parallel and you're offering up to the scheduler the opportunity to run those things in parallel. There's also concurrency, where you have a bunch of things that you want to demand will not block each other. They can run independently. So in one case, you're offering up parallelism, you're happy if it's taken up. In the other, it's kind of the dual. You're offering up independence that you demand the scheduler gives you. So these are like pretty different things. It's in fact tricky to build nice abstractions and nice runtime facilities that let you combine them. So there's a bunch of work on that. And then of course we have, a couple thousand people who would like to use this system and need to be taught how to use it. So there's a whole big teaching effort that we are like trying to do, in part by like explicit teaching. We're actually looking to hire someone to actually focus on the teaching aspect, if you know any names. And also just trying to like build the system to give people good feedback to help the tools teach people what's going on. So there's an enormous amount of work there. So stay tuned. Maybe in a few years we'll have a nice talk about how much dramatically harder this was than we expected, and various mistakes that we made and why it went terribly wrong. And if you'd like to watch the car crash in progress, we have taken all of this code and put it up and shared it on the internet where people can use it. So the OCaml has basically the full set of extensions to OCaml that we have developed internally. And it's in an interesting spot. It's like totally a production quality system. It is our production system. Every day, all of our stuff is running on this. When things go well, we release a new compiler every week or two. And like, there's a ton of stuff constantly going there, and like we kind of regularly kind of push this to the outside world. But it's not like exactly intended for other people's production use, because we are going to change stuff mercilessly fast, and like we're not going to help you keep up. Right? This is like a kind of compiler where we're like very excited to have, researchers and enthusiasts and stuff dive in and try and help us and like develop things there. But like, I don't know that I would recommend like betting your like very large company code base on this, because like we have control over our code base. When we want to change a thing, we will spend a bunch of effort and like write a mechanical refactor and like smash our 80 million line code base to behave in the way that we want. But those tools do not work on the outside, and we cannot like reasonably share them with other people. And so, I think, it's not the kind of system that you want to use at scale. I think like the primary purpose of all of this is like, this is a place where we can put these out and get feedback, and like over time, as these things stabilize, we hope to basically upstream all of this to the upstream OCaml compiler. Obviously, we have to like convince people that it's good. It's worth saying it's not good now. Like, it's complicated and messy. Like, we've done a lot. It's valuable. Like, it's worth it, but like the language is not in what we think of as a final state where like a lot of these language features are ready and stable enough to be upstreamed. But we expect to get there. I think the Multicore OCaml process took years. I think we expect this process to take years as well. Hopefully fewer. But yeah, I think we think it's like a fertile ground for connection to other people and researchers and people who kind of want to investigate. And we are like, contrary to our usual behavior, it's like documented, like, pages describing how the type system extensions work and all that. So hopefully it's like even if it's not a thing you want to, run your next startup on, hopefully it's a system that is a fun and pleasant thing to experiment with and try out and to learn from. And we actually think there's like a lot of fun and interesting ideas here that like, even if you don't care about OCaml per se, I think are probably relevant to lots of other languages out there that people are working on. All right, and that I think is all I got.
So it seems like you have solved the pacing problem, because your talk pacing was excellent. So we have at least 5 minutes for questions.
I really enjoyed that. If there's one thing we've learned from machine learning, it's that they have this culture of dynamic benchmarks. So they're always updating benchmarks, having competitions and so on, like Kaggle. And then they've also got this culture of sharing and remixing, right? So they release models and then they run them with these benchmarks. But looking at your timeline, we did a bunch of fixed effort for Sandmark. It was really, really thankless. And then it's pretty much unmaintained now, and you've got your internal benchmark suites. Should we be treating benchmark engineering as a first-class thing we do in language design? So why aren't there 100 different variations of the garbage collector? We've got one from KC that we heard about in this workshop, but they really are a rare thing, right? So should we really be having dozens running dynamically with people contributing benchmarks and having a bit of a competition all the time? This feels like an asymptotic way to speed things up.
So I think making benchmarks better is good. I think it's also hard. And I think in this case, like I think the first order lesson is not we needed a much, bigger community of people. I think the big lesson is really we should have designed the system in a way that made using real programs easier. Like you could have seen these, and we did see these slowdowns on like sufficiently large runs of like OCaml C, right? So I think these problems, in fact, were relatively coarse-grained and relatively easy to find. Not all of them, but a lot. But there was a lot of pretty big things that I think like the kind of like fine-grained sandmark approach just wasn't going to get, and that we mostly just needed more real programs. And I do think like we do have like a decent number of like open source real programs out there, and I think that some amount of, at least especially for these kind of coarse-grained things, if you're trying to do like really fine-grained optimization, benchmarks are super hard, and even internally at Jane Street, like in many ways we're kind of giving up. Like there's lots of places where people have built nice little benchmarks, but if you're trying to see is that like a 2% regression or a 3% regression, like often we're just we're moving in the direction of more instrumenting production and being able to like run production against multiple compilers and see, randomize which one is doing what and see, over kind of rolling out over time what the problems are. So I think depending on what your goals are for the benchmarking, I think you want to approach things different ways, but I certainly think we could like do better of having a public set of benchmarking that had more large-scale real-world tasks that would, I think, help us catch pretty easily coarse-grained issues. The fine-grained issues are like a deep problem that I mostly don't know how to really solve.
Yeah. So I was wondering if you could talk a little bit about managing this sort of software project, because while you are developing a completely new garbage collector, the world keeps moving outside, and you do need to keep what you're doing now up to date with, so that it can be merged in at some point, and when you have to go back and rethink the thing, redesign the thing, and all of that stuff. Whenever I've been involved in those types of things, it's a pain to keep it on track, to keep it aligned with all the systems that it has to work with.
I think that's a better question to ask the next time Casey gives a talk about this. Like this is like the whole hard work of landing Multicore OCaml. Like that's not what this is about. I didn't see that happened off in the background at at various OCaml labs and the like, and like we were very happy about the result, but we mostly didn't do it. In the future, we're going to try to land a bunch of stuff upstream. We'll see how that goes. It is saying like we do on our world. There is a bunch of work of like keeping up with even with our own branch, we want to keep up with upstream OCaml and like being able to rebase efficiently, thinking about if there are things that are very conflicty, then you want to like push towards upstream those pieces earlier. So I don't know, there's various things that we can do on the margin to make it a little easier, but mostly it's just hard work, is my sense.
So, yeah, I mean, you mentioned the sort of mammoth task of merging Multicore OCaml into, the thing that KC did, merging that into OCaml. I think there's a slightly different situation here, where at least, there were so many moving parts there, like changing to a concurrent garbage collector, the parallelism, effect handlers. For this, at least, that first 7-year part maybe doesn't have to happen.
I guess I gotta say the challenges of this work are different.
But do you still think it's going to be? When you said 7 years, this is 10 years, isn't it?
That's fair. So I think, what do I think about this? So first of all, we should upstream some things earlier. For example, a large fraction of this work on improving the pacing has already been upstreamed. The remainder of it is going to be upstreamed, right? And there are various pieces of our extension. So for example, polymorphic parameters and labeled tuples and various other things like that have already been upstreamed. I think the mode stuff, which is like the most important thing that kind of is driving this parallelism thing, is like it's still like, I don't know, 18 months from being worth upstreaming. It's just like, like it's just kind of bad in some sense, right? Like we don't like, maybe like the primary example of the thing that's like quite bad now is we don't have enough polymorphism in various parts of the system, and so we have like a horrifying like templating system that like allows us to programmatically like cut and paste many copies of the same function for different ways, and like we've got to fix that stuff before upstreaming it.
So in some ways that's actually worse, because there's to a certain degree there's a research problem there that needs to be solved in order to.
So yeah, there are some things that are research problems. There are some things that are just engineering problems.
But my point though is that on the other hand, it's a much easier thing because it's you're not affecting like the entire infrastructure of the compiler. You don't have to write a new GC in order to get that working. You just need to get the front end done. So maybe this will be quicker.
Yeah, I mean, I think, what do I think? I guess I'll say the actual work of making it work well is like hard work. And it's our experience thus far is it takes real time to do. And so I think, I don't know, I agree that like you don't have the same kind of like uncertainty around runtime behavior. And in many ways, I think there's some of the problems here are going to be social, right? Like, if you ask me what we're building, I think OCaml is like the analytic continuation of OCaml. It's like what OCaml wants to be when it grows up. It's like the natural set of features, you know, at least the thing we're aiming for. Now it's kind of, you know, grotty in spots, but like we're trying to think that feels to us like a very natural extension of language in the way that it achieves key features. Like OCaml is in some sense obviously in an uncomfortable state of it has the ability to run multi-core stuff, and it has no acceptable programming model. Like if we've learned anything from the process of trying to like push the data race freedom through is like reasoning about data races is subtle and they are not where you expect them to be, and having a nice type system discipline is good, and I think it's very hard to do it without. So I think in some sense OCaml really needs this to like fulfill the promise of the things that have already been built into it. But you know, you do have to convince people it's good. Me saying fancy things about how much I like it is like not going to cut a lot of ice. Like people have to see it being good. And I think it takes time to make make the type system stuff really effective.
So unfortunately, we are at time, and this is the last talk of Rebase. So thanks everybody for coming, and thanks Ron for your talk.